So let's start. Few announcements. So firstly, so next class we have the midterm. I sent around an email with instructions, but basically, as announced very early in the course, it's open textbook. You can bring a cheat sheet, one page, letter size, two-sided, has to be handwritten in ink, so you cannot do some microscopic photocopying and all. The whole idea is I wanted to go through the act of preparing the cheat sheet because it's very educational. So midterm are in 50 minutes. Out here, the TAs will proctor it, and you have to answer in the exam booklet itself. So answers written on any other paper or blue book and all will not be accepted. Let's see, you won't need any calculator or anything. In fact, no electronic devices are allowed. So any arithmetic that you're required to do would be simple enough for you to do directly. Let's see. Now, the style of the midterm, some of you had asked during office hours and stuff like that. So do problems at the back of the book. Problems similar to what we have done in the homeworks. So as you would notice, some of the problems I offer are kind of straightforward application of or very similar to what we do in the class, and some of them tend to have more of a design component where you really have to parse through a specification and then convert it into something that some Boolean logic that you have to implement. So you have both style of problems. If you have been doing the homeworks on your own, that would suffice, and try to do as many problems from the back of the book, or just look around on the web. There are plenty of example problems floating around and all, so they are good sources, or any other textbook in the space. Let's see. Solutions to problem set number 2. I just posted like maybe 20 minutes ago. So again, it's a Google Doc. You can, and just to clarify, you may not bring lecture notes. You may not bring homework solutions in the midterm. So it's textbook and the cheat sheet, nothing else. Okay, so any questions? Okay, now I guess the remaining thing is what else is included? Everything through adders. So there's a little bit of that we'll cover today. And then my plan is I'm going to walk through homework 2 solution. And then also along the way, we'll kind of just see possibly some other problems along the way. And if any of you have any problems that you would like me to solve on the board, you should. Problem set number 1, if you have any complaints, questions, clarifications, whatever about your grading, then first see the TAs and they will do their best to resolve it. If that fails, then only then I'll kind of intervene. So just to clarify, the problem sets are graded by a grader. The design assignments are being graded by the TAs, but the TAs will also kind of assist you on issues arising out of the problem sets as well. Okay, so there was a hand being raised there.
We can pick up the problem set at your office hours tomorrow.
Pardon me?
We can pick up the problem sets at your office hours.
Yeah, you should be able to. I don't have them with me right now, but I'll have them. So office hours at 4:30. Yeah. And also one more thing, I sent an email around. So I have changed my office hour schedule for this week. So instead of Wednesday and Friday, I'll have them. I have an extra office hour today. So 6:30 to 7:30. There's a gap of an hour because I'm teaching a second class and I have office hours from 5:30 to 6:30 for that other course. So today 4:30 to 5:30, 6:30 to 7:30, and then tomorrow 10 to 12. TAs have the usual office hours, and I'll probably ask them to kind of hold some extended office hours tomorrow as well. So just in case, yeah. Otherwise, rely on Piazza. I'm sure you have noticed we kind of are responding at all sort of odd hours also. So we'll try to answer to the extent we can. Okay, any other questions? Okay, well, so let's start on sort of the material covering. So again, the plan today is I'm going to wrap up adders. This will be in the midterm, so you do need to know adders. And we'll stop there and kind of go through the review. Okay, so we saw two things last time, full adder and half adder. And essentially, kind of the addition in the base 2 domain is very, very similar to what we do in base 10. So when we do multi-digit addition, we add in a single place, do a carryover, move to the next place. So in a regular arithmetic, we go from unit to tens to hundreds. It's the same thing out here. We go from unit to twos to fours and so on and so forth. And whenever you are adding two numbers, generally speaking, you are going to get a digit, or in our case, a bit at the sums place. And then you're going to get a carry of either 0 or 1. And then generally what you any bit other than the bit 0, what you're really doing is you're adding two digits and a carry. Now, the confusing thing in binary is that our digits are 0 and 1, and our carry is also 0 and 1, right? So in regular decimal arithmetic, at any arbitrary place, we get two digits, which could be 0 through 9, and then we get a carry, which is either 0 or 1. In binary, we tend to we have three things. So we have the bits of the two numbers we are adding, the corresponding bits, which are 0 and 1, so it's 1 bit, as well as we have a carry, which is 0 or 1, which is again 1 bit. So in any given bit position, we add 3 bits, 3 1-bit numbers, and that's what a full adder does. A half adder, by contrast, adds two 1-bit numbers, and half adder tends to be used in the lowest bit position, in the units place, where we don't have any carry coming in. We'll see later on that using a full adder even at that bit position helps. So half adder adds two 1-bit numbers. Full adder adds 3 1-bit numbers. In either case, our output is going to be up to 2 bits, right? If I add two 1-bit numbers, then in the worst case, I have 1 plus 1, which is 1, 0. If I'm adding 3-bit numbers, in the worst case, I have 1 plus 1 plus 1, which is 3, which is 1, 1. So again, a 2-bit number. And what we do is we think of this 2-bit number, we think of the least significant bit as the sum bit, because it goes right below the bits we were adding. And the most significant bit is the carry, which kind of feeds into the next bit position. So on Piazza, there was some sort of, someone asked a question and someone said, I think carry is 1 bit and sum is 1 bit. There's no ambiguity there. I mean, we are dealing with base 2. Our digits are 0 and 1. When you are adding in any place, the sum is going to be 1 base 2 digit, namely a single bit. And the carry is either 0 or 1, which is again 1 bit. So last time around, we saw the development of half adder. I'm going to go over that. You would have needed it for one of the homework problems anyway. Full adder also we saw, but I'm going to repeat that again. So full adder is taking 3 bits. And we call them conventionally, kind of A and B represent the 2 bits of the 2 numbers we are adding, and Ci represents the carry being fed to us from the previous bit position. But that is just nomenclature. You can think of it as just a third 1-bit number. So what we are really doing is we are adding 3 1-bit numbers. Our output, the numeric value of the output is given out here, and then binary representation is given out here. So you would see like 1 plus 1 plus 1 is 3, which is 1 and 1. The least significant bit goes right at the bit position we are trying to do the addition at, and this one is corresponding to the next position. So it's the carry out of our thing. We also saw the logic behind this. So if you look at the sum, it is high whenever the number of ones in the input is an odd number. So like for example, 0, 0, 1 has a single 1, which is odd number of inputs are 1, and therefore the sum is 1. Likewise, 1, 1, 1, we see the sum is 1. On the other hand, for let's say 1, 1, 0, it has 2 ones, which is even, and therefore the output is 0. So sum is a logic function. In this case, is a logic function which is outputting 1 whenever an odd number of inputs out of the 3 are high. And that defines an XOR function. An XOR gate's role is precisely to do that. It takes a bunch of inputs and it outputs a 1 if an odd number of them are high. So we can represent sum as a 3-input XOR gate, which can actually then be implemented as a chain of XOR gate. You can always show that if I do A XOR B and then take the result and XOR it with C, it's the same as A, B, and C XORing through a single 3-input XOR gate. The carryout, on the other hand, as we saw last time also, is really the majority function. It's high whenever 2 or more of the inputs are high. So 0, 1, 1 has 2 inputs high, 1, 0, 1 has 2 inputs high, 1, 1, 0 has 2 inputs high, and 1, 1, 1 has all of them high. And those are precisely the values for which carryout is 1. So it's a majority function, which we saw very early in the course also. And its implementation is A and B, or A and C, or B and C. Okay, so we've seen its implementation as well. So majority circuit looks like this, and you can convert. If I ask you to only do NAND gates, then how would you do it? Anyone? So I'm given this circuit, but let's say I only gave you NAND gates. Louder. This is sum of products, De Morgan's or duality. Yeah, actually, just change all the 4 gates to NAND gates. That's a good pattern to remember. Exactly. And the way it kind of works is you basically conceptually, on this wire, let's say, you put 2 back-to-back inverters, 2 back-to-back bubbles. One bubble goes to the output out here, the other one feeds to the input out here. And I do for the same all of the 3 wires. So these 3 become NAND gates, and this is an OR gates with inverting inputs, which is the same as an AND gate with an inverting output. That's where De Morgan's comes in. So even though majority, we are writing it as AND gate and OR, it's easily can be done with NAND as well. Okay, so now, and as to the XOR gate, like I already said, a 3-input XOR gate can be viewed as first XOR 2 of them, take the output, and then XOR that with the remaining one. Okay. XOR, if I don't give you an XOR gate, if I tell you you only have NAND gate or AND OR gates, then you have to look at what an XOR gate does. So what is the equation of an XOR gate? Let's say I have 2 inputs A and B. Then the output of XOR is, anyone? So there are 4 combinations: A, B, A bar, B bar, A bar, B, B, A, B bar. Which one? A bar or B? That's not entirely correct. It certainly is 1 when it's A bar, B. Correct. So it's A, B bar or A B bar or A bar, B. XNOR, on the other hand, is AB or A bar, B bar. So if you are given XOR gate, you can use it. If you're not given XOR gate, then you basically have to implement that equation using sum of products. Okay, so now this is one way of implementing full adder, but another way of implementing full adder is to make use of the fact that we already have learned how to do half adder. Half adder tells us how to add 2 1-bit numbers. Full adder seeks to add 2 3 1-bit numbers. So we can make use of that observation. So and it works out like the following. I'm going to skip to the final slide of this animation. So what we have really out here is, so I have 3 numbers now, A, B, and C in 3 1-bit numbers. I'm going to use a half adder to add 2 of these bits. the output I'm getting is sum and carry. And conceptually, what's happening is sum represents the unit position number, unit position bit, and carry represents the twos position bit, right? I mean, our output was a 2-bit number, carry was the more significant bit, and sum was a less significant bit. So when I added A and B using this half adder, I have this value P, which represents a bit for the units position. And G represents the bit for the twos position. I still have one more bit remaining, which is still at the units position. So I'm going to add P and C in because they represent, they both have a weight of 1 because they are both in units position. So I'm going to add them using a half adder. And this half adder again produces a sum, which we are labeled S. That again is units position. Whereas this output of the carry, which we are labeling as CP, is its weight is going to be 2 because it's in the twos position. Now I have G, which is at the twos position, and CP, which is at the twos position, and I have to kind of combine them. And you can. It turns out in this case you can do it with a OR gate, so you have a C out, and we can kind of work out for each various cases, and you'll see it works correctly. So let's take 1, 1, 1. So A is 1, B is 1, C is 1. So we have 1 and 1 out here. So let me kind of write it down. So we have 1 here, we have 1 here. So 1 and 1 is going to result in an output of 1, 0. Specifically, carry is 1 and sum is 0. C in was 1. So I'm now on this half adder, I'm adding 0 and 1. Its output is going to be carry of 0 and sum of 1. So this is going to be 0 and this is going to be 1. And now here we have 1 or 0, output is 1. Which makes sense. We 1 and 1, which is what we wanted according to our truth table also. And you can try out all the cases like this. Now this is something we saw last time also, and one of the homework problems actually also required you to make use of the same insight. So where I count problems went something like count the number of ones. So you could use 2 full adders to add 3 of them, and then I think there were 7 inputs, so there was 7th one remaining, and then you have to kind of combine them again. So main thing to understand is half adder and full adder are producing 2-bit results, which means that one of the bit, namely the sum bit, is the units position. The other bit represents the twos position, and you have to keep track of which bit represents what. Okay, I could not, for example, out here, if I had said, oh, I have 2 bits out here, let me add C in with this guy up here at the top. That will not be right because the weight for this guy is in the twos position, whereas this guy P was in the ones position, and so was this guy. So just like in the decimal one, when you are adding numbers, you have to keep things aligned. You can only add digits which have the same positions in the decimal system, unit, tens, hundreds. It's the same thing out here. You have to keep track of what's the right weight for a bit when you decide to add them. So full adder can be made using, in this particular way, using half adder. It turns out that adder obviously is a very, very commonly used operation. It's used in computers for internal purposes. For example, your program itself has a program counter. It kind of gets an instruction, gets the next instruction, gets the next instruction. So there's a register in every CPU which keeps track of where in the program you are. It's called program counter. And every time a computer executes an instruction, program counter needs to be incremented by 1. That's an addition operation. Likewise, when you are manipulating arrays and all, you have to kind of walk down the array. So you have to read an element of the array, then increase your index, read the next element, so on and so forth. So addition occurs internally in computers. Addition occurs a lot in our algorithms. So it's such a critical operation that, it just has to be there. You will it's available as an instruction. And moreover, it's usually one of the things which takes a long time in the combinational circuits. It's very highly optimized. So people have spent sort of countless amount of effort and all, coming up with better and better ways of doing addition. And by better, I mean circuits which are fast, take less area, are lower in power, and stuff like that. Once you have a good adder, then you can make a whole bunch of other things. Multiplication is nothing but addition of partial products. That's how division involves subtraction, which again is basically addition done up, addition with a negative sign. So this is an example, and I'm not going to go into detail, but it's a circuit which had been optimized quite a bit to create a fast adder. You don't need to know this. I don't expect you to know this, but just want to point out. Now, how can we do multi-bit addition? So we already saw kind of like 2 bits addition, okay, which is when we were thinking of the full adder in terms of 2 half adders, we were really kind of adding pairs of bits, some in 1's position, some in 2's position. But a more general multi-bit adder is very much like when we add decimal numbers. So like if I were to ask you to add, let's say, whatever, some decimal number, 739 to 64, what do? We add digits, so we do 3, we do a carry of 1. So see what happened, there is a number appearing out here, which could be any digit ranging from 0 to 9. So the sums position in this base 10 system would be a value which can be any of the valid digits, 0 to 9. In a binary system, it could be any of the valid digits, maybe 0 or 1. The carry, on the other hand, will always be either a 1 or a 0. So the carry is a single bit number. And then now, in the next bit, I'm adding 3 numbers. 2 of them are decimal digits, and the third is a carry in, which is either 0 or 1. So in this particular case, it becomes 10. So we get a 0, we get a carry out here. Then again, a 10, and we get this. So 1003. So first bit position, we are adding 2 digits. Other bit positions, we are adding 2 digits and a carry in. Now that's the story in decimal. In binary, since our digits are also single bit, so basically what you can say in first bit position, we have to add 2 bits. Or another way of saying is, I'm adding 2 bits and a carry, but the carry is 0. In other bit positions, I have to add 2 bits as well as a carry in. All of them are 1 bit, and that's a full adder. So that yields our addition structure, which is we are going to use a half adder in the bit position 0, and we are going to use full adders everywhere else. And this half adder doesn't have a carry in, so actually we don't even need to kind of write this thing. Half adder just doesn't have a carry in. So half adder takes the 2 LSBs, least significant bits, produces the sum, which has a weight of 1, and it produces carry, which has a weight of 2. Next bit position, we have a full adder. It's now taking A1 and B1. Each one of them has a weight of 2 because they are in the 2's position, as well as I have this carry coming in, which also has a weight of 2 because coming from the previous bit. I'm now going to produce a sum S1, and I'm going to produce a carry out. The carry out has a weight of 4 because it's going to get used in the next bit position, and so forth. I mean, it's basically replicating our in a base 2 domain exactly what I kind of did out here. This is another example of a bit slice type design. We saw bit slice designs for arbiter. We saw bit slice design for magnitude comparator. This is an adder. If I want to create an arbitrary size bit adder, I just have to stack n of these, in this particular way. And what it produces, excuse me guys, those of you are sort of, it's just disturbing the lecture. Okay, so what we have out here is when you add 2 n-bit numbers, you are going to get an n-bit sum, and you are going to get a carry out, which kind of makes sense. Again, when I add 2 n-bit numbers, if they are large enough, then there would be a carry output coming out. If, let's say, I only gave you full adders and say implement an adder like this, then all that means is my half adder is nothing but a full adder with a carry in of 0. So I could use a full adder in the least significant bit position also, and just tie in carry into 0. Actually, more importantly, I can also kind of feed another 1-bit value to carry in of the LSB, and now I can do operations like A plus B plus 1. Okay, or I can do operations like A plus 1, right, and set B to 0. So usually what you will see is that in this, instead of using a half adder, they actually use a full adder out here, and they let you control the C in. This just gives you a little bit more flexible hardware platform. Go ahead.
So CI would be S of N.
CI is conceptually S of N. You're right.
And,
But just bear in mind though, it's never made available that way because your computers are fixed size registers. Okay, so it's not like when I add two numbers, suddenly I have a larger register available. So usually the carry out is available as, if you have done in assembly language, CS33 for example, it's available as a condition code as opposed to a data value. But you're right, it's basically S of N.
and can you explain what you said about weight again? Like
About-
the weight of C sub 1.
Right. Okay. So each one of these things are representing sort of, this is least significant bit, and so on and so forth. Least significant bit in the binary system has a weight of 2 to the power 0. This has a weight of 2 to the power 1, and so on and so forth. This has a weight of 2 to the power n minus 1. This is our positional number system. When we learned decimal one, we talk about units, tens, hundreds. In this case, it's unit, twos, fours, and so on and so forth. So now, if I look at C of 1, or if I look at this bottom adder, what's doing is taking A0 and B0. A0 and B0 are in the units position, so they have a weight of 1. But then I'm producing a 2-bit number. I'm producing S of 0, and I'm producing C1, which is actually the next higher bit. So it corresponds to position for 2's position. Okay, so when I'm adding multiple bits, I have to make sure that I'm adding bits which are residing in the same weight position in our base 2 number system. Okay, there were some more hands raised in the back, so nope. Good. Okay.
What is bit slice there?
Bit slice is this way of designing things where we design for 1 bit and then we kind of stack things up. Okay, so we saw that in 2 other things earlier on when we were doing arbiter. We had designed a single 1-bit arbiter and then we had stacked it up. And then when we had designed the magnitude comparator, it was the same way. We had designed a single bit comparator and we had stacked it up. This style of designing, as we discussed a couple of times, has the advantage that I can design one thing and then tile it to create arbitrary size things. So you want me to design a 10-bit adder, I can just stack 10 of them. You want a 16-bit adder, I can stack 16 of them. I don't have to design from scratch. But it results in these long, in this case, the long delay path can start from here, go through all of these until the carry out. So the delays can be high.
A and B were different number of bits. We use 2 half adders. For example, A is n minus 1, and B is n minus 2.
You could. So let's say if A was 16-bit and B was 10 bits, then in the upper 6 bits you could use a half adder. Now the thing is, that luxury you will have only if you are custom designing something, right? When you're designing a computer, CPU for a computer, you're going to design it where A and B are both 16 bits. Then all that means is that the upper bits of one of them might be 0. Any other question? Okay, so as I was mentioning, that usually when they design adders, particularly in CPUs, instead of using a half adder out here, they actually use a full adder, and then they make the C in available to you also. So you can kind of say, so this hardware is capable of doing A plus B, that means C in is 0. It can also do A plus B plus 1, in which case C in is 1. So it just gives you a little bit more flexibility. Now, a little bit about using very much the same thing. So thus far our numbers are positive. It turns out numbers could be negative and still very much the same hardware kind of works. Now, then it becomes what are negative numbers, right? I mean, and as we learned very early in the course, bits are bits are bits. It's how we interpret them, right? I mean, if I give you some bit string 0, 1, 1, 0, it could be representing a color from a set of colors. It could be representing the number 6. It depends on how you interpret things. So when it comes to negative numbers, it's really about defining a scheme through which I can represent negative numbers. So I can give you a set of numbers. I can say, look, consider all integers from -10 to +10. And now you need to come up with a way of expressing them in the binary. And as back in one of the lectures when we were talking about different representations, we saw that some ways of representing are good, some are not. And good and bad here can mean a couple of things. Some ways of representing things need fewer bits, some need larger bits. And the other thing is, some ways of representing make some operation easy, some not. So for example, a very good example is from the homework that you just submitted. The last problem, we were representing card as the upper 2 bits being the suit of the card and the lower 4 bits being the rank of the card. And some of you from Piazza Milling realize that if actually we were to just swap the order, then it becomes a numerical comparison, and we already had the magnitude comparator for it. So I was expecting that you would kind of come up with something like that. So, so what that meant was that clearly a representation where the rank was the lower 4 bits and suit the upper 2 was inferior to the other way around, because the operation of comparison became much easier one way than the other. And it, I mean, all swapping required in this case is just some rewiring or relabeling. So it really is a zero cost operation. Same thing here. So as we think about like how do we represent negative numbers, we have to come up with a scheme which hopefully leads to good ways of doing arithmetic. My adders, multiplications, and all should be easy to do. That's why I mean these are numbers, and we are going to do arithmetic over them. So negative integers. Now there are many ways you could represent negative integers, and some of them come from intuition. So for example, one thing we can say is that what I'm going to do is I'm going to represent the value of the number the way we think about binary numbers, and then I will have an extra bit to represent the sign. So like let's take the number 10. We write it as 1010, right? If I want to represent -10, I will have now an explicitly separate bit to represent the sign. So now what I'll do is I'm going to take 5 bits. 1010 represents the magnitude, and the 5th bit is going to represent the sign, and we can say 0 means positive, 1 means negative. Okay? And this way of representing numbers is called sign magnitude. I have a magnitude separate, sign separate. So that's one approach. And it turns out this big advantage is we humans think like that. We think of sign separately and we think of magnitude separately. The problem though is it turns out that doing arithmetic on this leads to costlier hardware. Okay? In particular, to do arithmetic with this, you will need to have special cases that you'll have to handle. What if the sign is 1, I have to do something special, if the sign is 0, I have to do something special. So then sort of people found that there are other ways of mapping negative numbers to binary representation which work better. So again, let's think about, let's say I want to represent all numbers from -15 to +15. There are a total of 31 numbers in that range. So clearly I need 5 bits, right? Because my set has 31 things. I need log n, log 1 base, log 2 of n, so log 2 of 31, so I need 5 bits. But there are many different ways of mapping those 31 numbers minus 52 plus 15 to the 32 binary things that we have. And sign magnitude is one of them, but there are many, many others. So one of them, which turns out to be very powerful, is something called ones complement. And we'll shortly see. And there is another one which is called twos complement. Twos complement, again we'll see how it works, is the most widely used representation for negative numbers in binary when it comes to computer arithmetic. And the beauty behind twos complement is that same adder which we already designed to work for positive binary numbers also works if we were to just say, hey, those inputs, those n-bit inputs were not positive binary numbers, but they were twos complement numbers. They were signed numbers which also had a plus or minus. Adder doesn't change at all. It's exactly the same adder that we saw just a couple of slides ago. So twos complement turns out to be very powerful. I can do unsigned arithmetic or I can do signed arithmetic depending upon my mood. I don't need a separate kind of hardware for it. So twos complement is the most common representation, but we are going to look at all of them shortly. So let's take an example. Let's say we have plus 23 number. So 23 is binary, we know how to represent, so that's the magnitude. But now let's say I also want to represent minus 23. I want to represent negative numbers. So in sign magnitude, what would happen is, so 23, we need 5 bits to represent the magnitude, 1, 0, 1, 1, 1, that's 23. In sign magnitude, we take an extra digit and use that to represent the sign. So plus 23 becomes the magnitude 10111 and 0 for a positive sign. Minus 23 becomes same magnitude but 1 to represent a negative sign. So that's plus 23 and minus 23 in the sign magnitude. And again, as from a human perspective, this looks very clean. I have magnitude separately, I have sign separately. But now let's look at how twos complement works, which I said is the most commonly used representation. So the way twos complement works is, I'm going to, if I have a number which is negative, so minus x, where x is the magnitude and it's a negative number, so minus x, then what we are going to do is we are going to instead come up with a representation for 2 to the power n minus x. And that would be a positive number. And then I'm going to use my normal way of representing positive numbers. So whenever I see a negative number, I'm going to replace it by 2 to the power n minus x. And the resulting positive number is what I will express, and we say that represents minus x. And this stage sounds kind of a bit of a black magic, that what's the benefit? But let's see how it kind of plays out. But that's the basic scheme out here. That is, I'm going to again replace x. Take the if I have a negative number, I'm basically going to add 2 to the power n to it. So if it's minus 23, I'm going to add 2 to the power n, 32 to it, and that will mean 32 minus 23, which is 9, and I'm going to take the 5-bit representation of 9 and call that a representation for minus 23. So let's see how it kind of works out for some examples. So I jumped a few slides, but so let's say I'm interested in representing all numbers which go from minus 8 to 7. Okay, so from minus 8 to 7, the total number of integers are 8 negative numbers, the number 0, and 7 positive numbers. So I have a total of 16 distinct elements. And this is where one thing you would see is that I will have an asymmetry always, right? We like powers of 2, because if I have n bits, then I can represent 2 to the power n things. But the 0 creates complication, so I have to make a choice. do I represent more more positive numbers or more negative numbers? In this, in 2's complement, the choice is I will go from -8 to 7, or -16 to 15, or -30 to 31, depending upon how many bits we have. So in this case, I'm going from -8 to 7. There are 16 distinct numbers. I need 4 bits to represent them, right? If there are 16 distinct things in my set, I need at least 4 bits to represent them. And what we do is, we say that for the positive numbers and for the number 0, I use the normal 4-bit representation, right? So 0 is 0, 0, 0, or 4 is 0, 1, 0, 0, 7 is 0, 1, 1, 1. Those are just the normal representations, right? So I have used 8 numbers where I have used 8 of these numbers where the first bit is 0. But I'm still left with 8 other patterns, which go from 1, 0, 0 all the way to 1, 1, 1. And we map them to negative numbers the way it is shown in the circle out here. So -1 gets mapped to 1, 1, 1. So you start, 0 is kind of your anchor point. You go right, you are increasing. You go left, then what you do is you start with the all ones and then you walk down. So 2 is 1, 1, 1, 0, -3 is 1, 1, 0, 1, and so forth. And let's see if it works out. So remember, I had said that a negative number maps to 2 to the power n minus the value of the number, minus the magnitude of the number. So let's look at -3. So according to the logic I had said, -3 should be 2 to the power n minus 3, right? We are going to find the bit presentation for that. Now, what is 2 to the power n? 2 to the power n in our case is, let's see. Okay. In this particular case, if you look at this pattern 1, 1, 0, 1, that corresponds to 8 plus 4 plus 1, 13. And 2 to the power n is 4 in our case. 2 to the power 4 minus 3 is equal to 13. So what we are saying is, if I want to represent -3, I'm first going to add 2 to the power 4 to it. Whatever positive number I get, its 4-bit representation is what the -3, which is going to be represented out here. And you can check it for others also. Let's take -6. So -6, we are saying we are going to represent it as 2 to the power 4 minus 6, which is 16 minus 6, which is 10. So whatever is a 4-bit representation of 10 is what the representation of -6 would be, and you would see that is indeed the case. Let's take -8. -8 is kind of an interesting one. So if we are saying representation of -8 is going to be 16 plus -8, which is 16 minus 8, 8. 8 in 4 bits is 100, so it is 100 out here. And same thing for the other one. So this is just our way of mapping things. So again, for the positive numbers, they remain unchanged. The only thing is, instead of 16 positive numbers, I only go up to 7. I leave the remaining unused, and we map them to negative numbers the way kind of described out here. So again, positive numbers as they are, negative numbers, you add 2 to the power n to the negative number. Whatever positive number you get, think of its n-bit representation, and that would be your mapping. So any questions on this? So, go ahead.
Do we, what about one's complement?
I'm not talking about it. Okay. So how do you represent what?
15.
I cannot, right? So I have only 16 choices, right? Now in normal positive arithmetic, we went from 0 to 15. If I have 4-bit numbers, and I want to represent negative numbers also, that is I have 4-bit numbers which are 2's complement, then I will only go up to 7 in this case. So if all 4 bits, if with those 4 bits I was representing only positive numbers, I would have gone from 0 to 15. But now I'm only going to go up to 0 to 7. Okay, so to answer your question, if I want to represent 15, then I will need 5-bit 2's complement numbers, right? Because then in those 5-bit numbers, 15 would be 0, 1, 1, 1, 1. Okay, so because I have only the number of combinations I have to play with is decided by the number of bits I'm willing to allocate. So when you hear a computer has 32 bits, right? So one way I could use those 32 bits is all for positive numbers only, going from 0 through 2 to the power 32 minus 1, which is roughly 4 billion. Alternatively, I can say I'm going to take roughly half of them and use them for negative integers. So in that case, I will go roughly from minus 2 billion to plus 2 billion. But all I have is 32 bits to play with, so I cannot change. I mean, that is not changeable. I have 4 billion distinct combinations. Either I can take all of them and map them to positive integers, or I can map some of them to negative integers. And that's the same game we are playing out here. I have 4 bits. Up to thus far in the course, we were mapping all of them to positive numbers. We were going from 0 to 15. Now we decided that, hey, I want to represent negative numbers too, so I'm going to go from minus 8 to plus 7. I still have 16 choices. Any other questions before I dive a little further? Go ahead.
Why are there more negative numbers than positive numbers?
Yeah, so that's the point, because we have 0. It's the annoying thing, right?
Why can we not make one more positive number?
Good point. We could. The thing is, turns out the properties work out better this way, and my adder remains an adder, like my standard adder remains an adder. So you are saying, why not go from minus 7 to plus 8? Okay. It turns out that then adders don't behave the way they would like to. So it's really a practical consideration. It would be another very valid mapping, and so can the other, sign magnitude, 1's complement. They're all kind of different ways of mapping things. Okay. But it just turns out that people found very early on, some 3-4 decades ago, they found that 2's complement leads to some very nice properties so that we can reuse our existing argument. Any other question? Okay, so 2's complement. Okay, now going back out here. So 2's complement has some interesting properties. It makes subtraction very, very easy. And the reason it makes subtraction very easy is the following, that remember, we are representing a negative number as, so if I have a negative number minus x, then in 2's complement, it is really the 2 to the power n minus x. Positive, it's the bit representation of 2 to the power n minus x. Now let's say, moreover, remember when I'm adding 2 n-bit numbers, the carry out which comes out gets discarded, right? Because I add 2 n-bit numbers in computers and I get another n-bit number. The carry out is thrown away unless you pay attention to it. What it really means is that I'm doing modulo 2 to the power n arithmetic. So what I mean by that is the following. Let's say I add, let's say I'm doing 4-bit, I have 4-bit adder. And let's say I add 1, 1, 1, 1, and which is 15, and I add 8 to it, which is 1, 0, 0, 0. Okay, so let's say I'm adding this 1, 1, 1, 1 to 1, 0, 0, 0. What would be the answer? 1, 0, 1, 1, 1. But we are only looking at the lower 4 bits. The carry out gets thrown out because in computers I have registers which are a fixed number of bits. So I added 1, 1, 1, 1, which is 15, 8. I would expect 23, which is 1, 0, 1, 1, 1. But since I ignore this thing, I'm actually getting 7. Right? If I only look at the lower 4 bits, that's 7. And that's nothing but, so this should have yielded 23. 23 mod 16 is 7. So when I add two n-bit numbers, I get an n plus 1 bit number. If I ignore the upper bits, then the remaining n bits are really the answer modulo 2 to the power n, right? I'm just throwing away the most significant bit. So we make use of that property, which is what makes subtraction easier. So this is how it works. Let's say I have x, and I'm going to do a subtraction, which is another way of saying is I'm going to add x plus some negative number minus y. Now we saw that minus y in 2's complement has the same bit representation as 2 to the power n minus y. And I'm doing the addition, but this addition is modulo 2 to the power n. So this 2 to the power n will disappear, and I would be left with, so this is the same as the magnitude x minus the magnitude y, because this 2 to the power n will disappear because of the mod part. So basically what it is saying is that subtracting, if I add a positive number and a negative number in 2's complement, just my regular adder works. I don't need to do anything specific. I just take my regular n-bit adder, and that will still work because negative number is represented as 2 to the power n plus 2 to the power n minus the value of that number, and this will disappear because of the way the adders work. So let's see, we do 4 minus 3, and let's say I have 4-bit arithmetic. So I have 4-bit 2's complement numbers. So firstly, with 4 bits, the 2's complement numbers go from what range? What's the most negative 4-bit? What's the most negative 2's complement number that I can represent in 4 bits? Negative 8, right? We saw that wheel earlier. And the most positive number I can represent is 0, 1, 1, 1, which is 7, right? So clearly I can, 4 and minus 3 are both representable. They fall in the range. So 4 minus 3 is the same as saying it's 4 plus 16 minus 3, right? So now in 4-bit terms, the 16 minus 3, modulo 16, which is the same as 4 plus 15 minus 3 plus 1, and you kind of add these things up, you'll see that you end up with 0, 0, 0, 1, which is a positive number 1. So so here 4 is 0, 1, 1, 0, 1, 0, 0, 15 is 1, 1, 1, 1, minus, then 3 is 0, 0, 1, 1, and then plus 1, and you kind of do this arithmetic, you end up with this. So subtraction, or another way of saying is adding a positive number and a negative number, just magically works with the same hardware that we previously designed for unsigned arithmetic.
Why did you do the second step?
Why did I do the second step? Because 16 cannot be represented in 4 bits, right? So I broke it up as 15 plus 1.
But then we have to ignore the carry out as the most significant bit.
Right. That is the modulo part out here, right? I mean, so what happens is when I add 2 n-bit numbers, I'm only going to look at the n bits. I'm going to throw out the carry out. Okay. It turns out that carry out later on in the course you'll see has some value. It tells me something about am I adding 2 very positive numbers so that there is an overflow. But for now, just imagine I'm adding 2 n-bit numbers, and I'm just going to retain the n-bit results. I'm going to ignore the carry out. So with this 2's complement, subtraction kind of works out very well. We have a strategy for representing negative numbers, which again are the same wheel that I had shown before. So what it means is that just by reinterpreting what, if I give you n bits, normally when we do unsigned arithmetic, so if let's say if I give you n bits, bn minus 1 to b to the 0, right? Normally, we think of them as numbers which are all positive numbers. And therefore, we say that they represent sigma bi 2 to the power I going from 0 to n minus 1. This is when when we think of them as unsigned. Right? This is a classical way of thinking about a bunch of bits as a number. But if we take the same bits and we think of them that, hey, they are representing 2's complement numbers, then really what we are doing is this. This is if as 2's complement. And this is an important point. So again, going back out here, let's say I give you a 4-bit binary thing, a 4-bit input. And if I ask you, let's say that 4-bit input was 1011. If I said it's unsigned number, then 1011 is 13. Am I right? 1011 would, sorry, 11. But if I tell you it is a 2's complement number, then the same 1011 is now interpreted as -5. So it's all in our interpretations, right? There's nothing intrinsic about a particular bit pattern to mean any particular thing. It's how you choose to interpret it. So if we choose to interpret those 4 bits as unsigned binary numbers, then we say 1011 represents 11. If we choose to say that, hey, I'm going to interpret this thing as 2's complement, then the same 1011 represents -5. Okay, and as long as you're consistent all through, things work out. It's only when you begin to mix and match that you have to be careful. But if everything is 2's complement, things work out great. If everything is unsigned, things work out great. When you mix and match, things start getting problematic. And so computer arithmetic, our computers usually support both the things. So like if you have programmed in C or C++, you would notice that when you're declaring an integer, you can either say int x or you can say unsigned int x. Anyone seen this stuff? Like unsigned, right? All that is saying is telling that use the instructions which correspond to unsigned arithmetic versus signed arithmetic. Okay, so that's all that's happening. But internally, it's the same 32 bits. How you are interpreting it. So, so that's 2's complement. Let's see. Yeah, I'm going to stop out here on the lecture part, I mean, and kind of going to. So what we have seen from thus far in this module is half adder, full adder, n-bit adder. That how we can interpret the same number 2 ways. We can interpret the same number as positive and the same number as 2's complement. Now, as far as the midterm is concerned, you don't need to know the 2's complement part that I just discussed. So up to the n-bit adder part, right? So how to use half adder, full adder, and how to do unsigned arithmetic. Okay, so what I wanted to do next is, so before I I was going to go through the homework, but are there any questions that anyone has that you would like me to kind of answer, perhaps from the book or otherwise? Okay, sounds like.
I have one.
Oh, go ahead.
I know, so in the notes you said that doing a K-map for an n-bit number greater than 4 or 5, I forget what number, was difficult, and you said that there was like a different method that works better for that. Can you explain that again?
Okay, so if I have more than, so we saw K-maps for 4 inputs. K-map for 3 input, I think I had in one of the homework, so it's a K. K-map for 5 input and 6 input. In the book, or some books, I don't know about this particular book, they often do it in terms of multiple K-maps, but it starts getting pretty hairy. So there is a method, the computational methods that algorithms use to kind of cope with these things. And the thing is, they're not designed for humans. Okay, so I'm not going to walk you through them, but roughly speaking, what they do is they represent functions as expressions, as Boolean expressions. But internally, the Boolean expression is represented as a particular type of graph data structure. It's called binary decision diagram. Okay, you don't need to do that. And then algorithms manipulate. They're basically doing computer algebra. So I'm not answering your question, but the thing is, those methods are not really meant for you. Now, what if you are faced with having to design a 5-bit or a 6-bit number? You basically have to do the Boolean equation where you can always write sum of midterms kind of representation of function and do some algebraic simplification of that. That's kind of like what the computers are internally doing, but they do it in a very systematic way with good algorithms. Okay?
Multiplexers in lecture, you often use it like input a binary selector, and then you have like 1, 1, 2, like single bit for what it's selecting. So it's basically like a yes or no kind of like, is it true for this? In discussion, we would often use multiplexers like what it was selecting would be like a multiple input kind of thing. So I was kind of wondering if you could talk about the different ways we can use multiplexers.
Sure. Okay, so good point that you raised. Okay, so I'll come to that while. Okay, any other questions? Okay, so let's take the multiplexer one because I think the homework already provided one type of example there. So okay, so I'm picking the very last problem to illustrate one use of multiplexer, and then I'm going to talk about the other use a little bit later. So the homework problem was the following: that I'm designing a system to for a card game. I have 4 players. Each one draws a card. That card is represented as a 6-bit number, in which the suit of the card is indicated by the upper 2 bits. That means whether it's club, heart, spade, whatever. And the lower 4 bits, that is bits 3 to 0, represent the rank, namely whether it's 2, 3 through ace. Ace has the highest value, as in normal cards. And the particular assignment I had given was deliberately made to keep life easy. So A was 1, 1, 1, 0, 2 was 0, 0, 1, 0. So we were not using anything lower or anything higher than that. So the observation out here in solving this was that a card, the winning card, is really, so I have 4 cards, I have to find the winner. So first thing I can do is find a winner on one pair of cards and find a winner from the other pair of cards, and take the 2 winners from this initial step and find a winner among them, right? I mean, so that part is easy. I can do winners 2 at a time. So I basically said the winning card, the card output, which is the winning card, is the winner of the 2 individual winners. So I'm going to imagine I have some function that I've implemented, f sub winner. I'll apply f sub winner to the card from player 0 and player 1. And likewise, I'm going to apply it to the card from player 2 and player 3. I'm going to take the 2 winners and then feed them to another winner module to select the winner. So that will tell me the winner card. It will not tell me the ID of the player, but it will tell me the winning card. Now, a little reflection shows, and actually, I mean, some of you came up with it also, that this f winner is nothing but a max function if I were to shuffle the bits in the card a little bit, right? So currently what was happening was in the card, the suit was in the upper bits and the rank was in the lower bits, but I really want to prioritize the rank over the suit. So we have to do a swapping. So if I were, so I can implement this winner function by essentially doing a swapping, which is actually kind of like a left rotate by 2 function. I basically take the upper 2 bits and feed them from the on the least significant bit side. So I can think of this winner function to be nothing but a maximum done over the 2 inputs after they have been rotated by 2 bits, left rotated by 2 bits. And this rotation function is nothing but a rewiring function, so it doesn't count against a logic gate. And max we have already seen in the lectures before. If you recall, we implemented a max of 2 functions, as being implemented through a 2-to-1 multiplexer and a magnitude comparator. So we can use the same strategy out here. So this is the solution that I came up with, and I'm pretty sure your solutions would be similar. So firstly, that rewiring unit, which is rotate left by 2, is nothing like this. It takes 6 bits, and it takes these lower 4 bits and moves them to the higher 4 bits of the output, and takes these 2 bits and moves them to the lower 2 bits of the output. So we are just doing the swapping. So just rewiring is an app module that I just labeled as rotate left by 2. And now what I'm doing is essentially, so I think things got chopped up a little bit out here. We have P0, P1, P2, P3 out here. So what I do is I take P0 and P1, and I modified the circuit from the lecture where instead of feeding them into magnitude comparator straight away, I feed them after I do that rotate by 2. So this rotate by 2 is now going to give me the winning, which card is the winner among these two, P0 and P1. I'm going to use that to then further select one of the 2 cards, right? So the 6 bits of this part from P0, 6 bits of card from P1, I feed it into a 6-bit mux. So out here, at the output of this top mux, I have the card which is the winning card between P0 and P1. And this bit, which is the output of the magnitude comparator, is telling me who won between P0 and P1. If this bit is high, it is telling me that P1, one party won. If this bit low, the other party won. Okay. I do the same thing between P2 and P3. So at the output of this mux, I have the details of the card between P2 and P3 which won, and on the output of the comparator, I have the identity of who's the winner among P2 and P3. Then what I do is I take the output of these 2 mux and play the same game again. I select which one of those 2 is the winner by again kind of keeping the same kind of structure. I have a magnitude comparator with this rotation and a mux. So what I'm doing is, if you think about this mux, actually if you think about this whole structure, what it is really implementing is, if any of you use Excel thing, is implementing the function if some condition so I have a condition, in this case, which is the greater thing, that A greater than B. And so in Excel, we have this function which takes if and evaluates a condition. And then if the condition is true, the output of this whole statement is true value. Otherwise, it's a false value. True value is an expression, false value is an expression. What we have really is a special case out here which says if my condition is nothing but A greater than B, and if it is true, then A, otherwise it's B. That is the structure that a magnitude comparator together with the mux implements. Okay.
Does your mux be binary? Because it only takes 0 and 1 instead of 0, 1, and 1, 0.
What do you mean? It's a binary select mux?
Is it a binary?
Yeah, it's a, and you can tell, right? I mean, it takes taking one control input. There's a 1-bit thing. So anytime the number of control inputs, the ratio between the number of data inputs to control input is n is to log 2n, then it's a binary select. If it is 1 is to 1, it's a one hot type control. Okay, very rare to have one hot control type muxes. Okay, it's usually binary select muxes. I think Logic is also all binary select. If I'm not wrong, I think it's binary select here. So it's far more common to have binary select mux. But always by looking at the wiring, you can kind of infer it.
Are you going to place any limits or take points off, like based on how many gates that you use on the midterm?
If I ask to minimize gate count, then I would. If I don't, then unless it's insanely inefficient, I won't.
Yeah, because I split the 4 and the 2 on this problem, so it got messier than that. But
Say it again?
Like I did a comparison on the lower 4 bits and the upper 2 bits separately.
Yeah, that's fine. Actually, it probably didn't increase the. It only increased the drawing. I don't think your solution affected the date count.
Okay.
So. Okay, so what we have out here is essentially this kind of a structure represents if A greater than B, then A, otherwise B. Now, in languages such as C and C++, there's something called a switch statement, right? I mean, what you do is switch on something, and then you say case this, do this, case that, do that, and you can have a bunch of cases. So, kind of to answer the original question, MUX, which is let's say 4:1, is capable of handling 4 cases. A MUX, which is 8:1, is capable of handling 8 cases, and so forth. So you could imagine, for example, I could take, if I have, let's say, 4 possible inputs, I can feed them into something other than a magnitude comparator, something more complicated, which outputs 2 bits, telling me something about those 4 inputs, and then I can have a 4:1 MUX out there, so kind of a more complicated thing. Now, having said that, conceptually, you might find for problems like these, to break them down into a series of binary choices and kind of work off that. So I could have, for example, implemented the system with a 4:1 MUX, where these two, all the 4 were feeding into a 4:1 MUX, 6-bit 4:1 MUX, and then instead of a magnitude comparator, I would have probably kind of something more complicated, and the output of that would have been 2 bits feeding into this 4:1 MUX. So this is what I mean. I could have implemented the system as okay. So I could have implemented that system as P0, P1, P2, P3. And then I could have some complicated decision logic out here. Which would decide which one of these 4 is the largest, and then feed its identity out here, and then that will let me pass the card through. And this complicated logic will nothing be but a series of decision making. So I can compare, I would have 3 magnitude comparators. So what I can do is, I can do magnitude comparison, another magnitude comparator. I first compare these 2, then I compare these 2, and based upon this, as well as I'll have to compare additional stuff. So I'll not go into detail, but you kind of work out some logic out here whose output would indicate which one of the 2 are winner, and then I can feed it into this 4:1 box. So it's just that it turns out to be more complicated this way. So break it down into smaller steps and do it. One thing I would like to emphasize is when you are faced with problems like these, don't dive into the circuit first. Think about the algorithm. It's pretty much like writing a piece of software. You have to first think about the problem. What is the approach of solving it? Mapping it to gates is easy once you have a simple clean way of expressing the algorithm. So think about that first. Usually what I see is students get lost because the moment they see it, you remember, in the class we had mux and all. So you start drawing muxes and comparators randomly and kind of hope that somehow magically it will yield the right answer. It doesn't work that way. There will always be some twist or something in each problem, and you have to kind of think about it. Now, the twist in this problem was that I also asked for the ID of the player. And so that you also need to output. So the way I kind of did, and there are a couple of different ways. So the way I did was I said, look at the output of this magnitude comparator and this magnitude comparator. It tells me within P2 and P3 who won, and the top one tells me within P0 and P1 who wants. And then the magnitude comparator out here tells me winner was in group P0, P1 or was it in P2, P3. Now, if you think about it, this magnitude comparator is telling me whether P2, P3 won or P0, P1 won. So it's giving me the upper bit. So the output of this magnitude comparator out here is nothing but my ID 1, the upper bit of the ID that I need. And I can use this to then select, do a group select, and if ID was 0, that means the winner was among P0, P1. So then I just pass through, I have a single bit 2:1 multiplexer out here, and I pass through to get the ID 0. So that's one approach. The other approach I thought was that what I could do is I can use these mux, but instead of 6 bits, I can carry an additional 2 bits, which also carry, which are the ID. So I'll take this P3 5:0. I will map it to P3 7:0 and make bits 7 and 6 to be hard coded to be 1. And for P2 5:0, I'll add 2 more bits, P7 and 6, and hard code them to 1 and 0, and so on and so forth. And then when I get the bits out here, I'll get the upper 2 bits. That would be the ID. It's less efficient, this latter approach, because I'm using this complicated muxes to kind of make things happen, but that would kind of also work. So again, sort of faced with these kind of problems, you have to first think about it, come up with a strategy, and then say, look, after all of this, these are the functions I need to implement, and then go around doing it. And your friends are things like muxes and magnitude comparator. It's kind of like you're writing a program. This thing is nothing but saying, if something, select this, otherwise select that. It's your if statement in a program. And then when you are chaining them together, what you're really doing is you have one if statement followed by another if statement. So you're really kind of writing a program using these building blocks. So go back to your CS31 and wherever you learn programming, that's going to help you tremendously out. Questions on my approach, or did anyone else have like another kind of question?
I just have a question about ID. Is it because we are comparing 0, 0, 0, 1? They're one pair. The 1, 0, and 1, 1, they're another pair. And then after that, how do we get the
Well, so again, I had group P2 and P3 together. So if the winner is in this group, that means the upper bit of ID has to be 1, right? And so, and then this comparator is deciding which group the winner lies in, right? This comparator is telling me that, okay? So that tells me the one part. And again, must emphasize, much like any problem that you're writing a piece of code for, there is no one algorithm. I mean, you can all have many different ways of approaching it. One person may like to think about a problem one way, another person a different way. It makes it harder for us to grade these things, but that's the very nature of the problem. The thing I want you to learn about is that faced with these kind of messy looking description, your first task is to come up with a strategy, the algorithm behind the hardware, okay, before rushing into implementing the logic, okay. Messy algorithms can create a very complicated circuit, and so kind of spend some time up front before diving into the solution, thinking about the strategy.
But what about ID 0?
What about ID 0? So ID 0 basically is telling me within a group who's the winner, right? So if ID 1 is 0, then I have to select if 5 is the winner, if P1 is the winner, then bit is 1, lower bit is 1. If P0 is the winner, the bit is 0, right? So this guy is telling me which one is the winner. It's 1 if P1 is the winner, it's 0 if P0 is the winner. And same thing out here. Okay, so let's look at, let's see which next problem. Okay, so let's look in the similar way in kind of this problem. I'm given 3 8-bit inputs, A, B, and C, and I need to find the output which is the largest of the 3. So this basically boils down to inside that max of ABC is max of AB, take the result, and then use another max function and the remaining number and do the max of that. We had seen the max again in the lecture. So this is really a simpler version of problem 8. A much simplified version of problem 8. Same strategy works out here. So this structure, magnitude comparator and mux, is basically saying if A greater than B, then A, otherwise B. And that structure is what we end up with. So this intermediate results is giving me max of 2 of them, and then I kind of... so you should be comfortable doing these kind of problems, where I'm giving you a bunch of numbers, unsigned binary numbers, and I ask for selecting something out of it. Could be minimum, maximum, median, second largest, second smallest, stuff like that. Okay, these are all different ways of kind of selecting something with a particular property.
So the magnitude comparator is always going to output 1 bit. It's going to be 0 or 1.
It could be 0. It could be 0 1 depending upon who won.
It will never be 2 bit 1.
Not the magnitude comparator we have done in this class, right? Because it's comparing 2 things. Now, you could imagine other types of magnitude comparators, and you could define them as your own building block. Like, for example, sometimes they show 2 outputs of a magnitude comparator. One will tell whether A is greater than B, and the other will tell whether A is equal to B. Okay? So those are just special cases, but kind of basic. You do not have magnitude comparator which compare 3 numbers or 4 numbers. They are just comparing 2.
Does it matter which input for the multiplexer we label as 0 or 1?
No, as long as you're consistent. Okay, as long as, and so like in the card example, you have to know the right one is getting set.
Consistent means, say that 1 will be on the top, 0 on the bottom.
Yeah, I mean, whatever you're comparing is the right one you're selecting. Right? Oh, are you referring to when I'm drawing it, which one is 0, which one is 1? Okay, so I guess I myself did not follow my dictates, but I tend to use 0 at the top, 1 at the bottom. Okay. You are supposed to do that. Any questions on this style of problems? Yeah. Huh?
I had a question about a different problem.
A different one? Which one?
Just like number 6. Looks like.
Yeah, let's go to number 6. Okay, so 6 is a fair arbiter problem. By the way, I didn't expect you to write all of this. This is just so that you understand my solution. Okay, so I sort of took the time to kind of write some explanation. So fair arbiter, the problem we have is the following. In our original arbiter, we had a circuit which basically would always start from bit position 0. Will give bit position requester number 0 the highest priority, and then if requester 0 was not requesting, then it check for requester 1, and so on and so forth. And what the problem asks for is that now instead of just giving you the R vector, R as the input, I'm also giving you an additional input P, where P of I indicates that I was the winner the previous time around. And therefore, first I should check I plus 1, I plus 2, and then back. So I want to give the winner of the previous round the least priority in this round. So one thing it immediately suggests is that I have to roll around, right? I mean, if let's say I had 4 requester, and if in the previous round requester 3 was the winner, then in this round I have to check in the order 4, 0, 1. 3, 0, 1, 2, in that order. If in the previous round requester 3 was the winner, then in the current round I'm going to check 0, 1, 2, 3. If in the previous round 1 was the winner, I'm going to check 2, 3, 0, 1. So that's going to be the order. And in our original design, at bit 0, so the basic structure of our design was that we had this 1-bit entity where I was taking the request, I was generating the grant, I was getting no one yet from a previous stage, and I was generating a no one yet for the next stage. And I always had no one yet for the 0th stage tied to 1, and then I kind of started from that. But now I need to be willing to start this chain of no one yet from any arbitrary bit position, depending upon what P is. So one solution is that what I do is I effectively kind of put a logic out here, where what I'm saying is, if Pi is high, then no one yet feeding to the I plus 1th stage is going to be unconditionally high, which basically means I'm going to give that guy the highest priority. And the chain will, so there is no effect. If Pi is high, then there is no effect of the output of the other input to this OR gate. And I kind of structure it like this. So like think of it. So one thing we know is only one of Pi will be high. Rest would be 0. So if in my example, let's say P of 2 was high, that would mean that this bit position 3 will see a 1 out here. So my whole priority arbitration will start from 3, go back, see how I have this thing going back, and then it will work this way through 0, 1, and 2. So I give priority to 3 in this case. If on the other hand, in the previous round 3 was the winner, then P3 would have been high, in which case bit position 0 will see a 1 coming in, and it would behave like our normal arbiter. So we are making use of the fact that one and only one P is high. There was a question on Piazza, what if there was no winner in the previous round? And I guess what I responded was, keep life simple, assume that there's always a winner, and that was selected. Now, looking at this, something should trouble you, which is in one of the very early lectures, we had said loops cannot be there in combinational circuit, right? Or the more precise statement was, if there is a loop, the circuit may have memory. That was kind of a statement from, I don't know, lecture 2 or 3. But remember, the statement was, if there is a loop, the circuit may have memory. It doesn't mean does have memory, okay? So it doesn't mean that every circuit which has a loop is necessarily not a combinational circuit. This is an example where it is not, and the way to reason about is the following, that if, for example, P2 is high, so let's say P2 is high, then this OR gate, its output is tied to high. So my loop is broken out here, right? I mean, loop is bad only if an effect flows through the loop. But if, in this case, if P3 is high, then it's as if I have tied this output to high. And therefore, we really do not have a loop out here. Okay, but it's dependent on the observation that at least one P, or actually precisely one Pi is high. If that wasn't the case, if P's could be arbitrary, then this circuit would behave as if it may have memory. In particular, if all the 4 P's could be 0, then this circuit would have trouble because we'll have a combination loop forming. So there's a tricky circuit, and I wanted to kind of analyze this thing that not all loops are bad. Okay, this circuit, given the specification, namely there is a winner, the previous round, is going to behave fine. Now, I used this logic out here. You could implement the same thing using a couple of essentially creating a mux with a couple of tri-state buffers, which is why one student had asked for it, so I kind of made it okay to also use tri-state buffers, so you could use that. Same logic out here, so what's happening is if P0 is high, I feed a 1 out here and disable the other tri-state. If P0 is low, then whatever the previous stage was providing kind of flows throughout here. So a couple of different ways. You could also use a mux, really, also a 2-to-1 mux controlled by P0. So there are many ways of implementing this, but that's kind of a basic idea. An alternative, given that we had only, I guess in this problem I asked you to draw for only 4 bits, so you could create from scratch a truth table and kind of design it. It would be, you have 8 inputs total, you have 4 inputs of R, 4 inputs of G, and 4 inputs of P, and you can write down the equations and kind of create a circuit, perhaps use Logisim to synthesize it for you. It would not be quite in the spirit of the problem because the idea here was that I wanted it to develop a scheme and then show it on a 4-bit example, not just design for a 4-bit case. So if you did it that way, that is, you just designed a hard-coded 4-bit circuit and did not present a strategy on what would it look for other number of bits, you'll get partial credit on that. So any questions on this one? So, couple of things I would like to emphasize. Number one, be comfortable with these designs or these modules where things go from bit to bit. Okay, we have seen several of them. We have seen the n-bit adder. We saw the arbiters. We saw the magnitude comparator. Okay, so this kind of bit sliced way of designing is useful thing in digital design to know, and so you should be very comfortable with that. So try to look for problems, to solve for problems along those kind of things. And the other thing is, be comfortable kind of synthesizing bits and pieces we have learned in different places to bring it together. Because a naive reaction to the circuit is loops, there's something wrong. But if you just go a little bit deeper and analyze what's happening, it's actually a combinatorial circuit. Can I go over priority encoding? Okay, let's do that. Let's see, how are we doing time-wise? So we are at 3:32. Okay, so let me do your priority encoder. Okay. So priority encoder is an example of kind of picking 2 modules and kind of creating something more complicated behavior out of it. So what a priority encoder does is it's defined as something which takes 2 signals, an n-bit signal A, it outputs an m-bit signal B, where B indicates where does the first one occur in A. Okay, so the idea is that A has n bits, some of them are going to be high, some of them are going to be low, and if A has n bits, then the bit positions of A can be represented in log 2 n bits. And so the idea is that we want the output to indicate which bit position has the first one, as we start from, let's say, the least significant bit in this case. So
what's the difference between this one and arbiter?
An arbiter just tells us who the winner is. So arbiter would have of these, whosoever is the winner. The arbiter we did was starting from the first one, so it will walk from the LSB. It will say, so the first one it encounters, that's the winner. But I'm outputting an n-bit number, a 1 hot coded number. Whereas here, I'm outputting a binary coded identity of winner. So the difference is that priority encoded winner is telling me in a binary encoded form.
So this is the position, that one actually gives me the winner.
This one tells you the position of the winner. That one tells you of the n1 which one is highly coded. So it's 1 hot coding versus binary.
So do we have to do like a start from the LSB?
That's the spec out there. Okay, but imagine I could have given you a variant of the homework problem where I would have said design a priority encoder where I also give you the winner from the previous round.
I I mean, like when we use the building blocks, do we assume that start from the?
Yeah.
It's always from the.
Yeah, always. So again, for purposes of our homeworks and exams and all, the valid building blocks are the ones which we have used in the lecture. And for purposes of the design assignment, the valid building blocks are the ones which Logicin provides, and which kind of tend to behave somewhat differently.
So, what is the point of this?
What's the point of this? What it would be using, because like for example, let's say a bunch of processors are requesting a resource. I decided that they are sorted in priority. Processor 0 has the highest priority, and so I'm identifying which is the processor requesting a resource and has the highest priority, and then I'm giving out this ID, as opposed to having a line per processor and activating one of them, right? So really the difference between priority encoder and arbiter is, in arbiter the output is an n-bit output where n is the number of requesters. In this case, I have log 2n bits, which is indicating what is the ID of what's the bit position or ID of getting in. Okay, which is why you basically see that priority encoder is implemented as an arbiter followed by an encoder. That's literally what it's doing. It's taking, arbiter is producing a one-hot coded representation of the winner, and I'm then encoding it. To get a binary encoded.
So, for your example, there would be n processors, each sending either a 0 or a 1.
Right. Each raises a line. So from each processor, there's a line coming in to this priority encoder. Some of them are 1, some of them are 0. Priority encoder starts from processor 0 onwards till it hits the first processor which has raised this line, and then it is supposed to output the ID number of that processor. Whereas the arbiter was sending back a line to each one of the processors and raising one of them. Okay. Any further question on kind of the arbiter, priority encoder? Okay. Let's go back to the homework so that we can. Let's see. This problem where I wanted you to find, so you were given A, B, C, D, E, and F, 6 inputs, and you had to output 1 if an even number of them were 1s. Okay, so the idea is if let's say A and B are 1, the rest are 0, then 2 of them are 1, so the output should be 1. Okay, and we already saw for XOR gates. They tell me when the number are even. So XOR tells me when the number of inputs that are high is odd. So XNOR is the other way around. It gives me the even one. So this is really about XNOR, and then you basically gang up XNOR. What I'm really creating is a 6-input XNOR, but I didn't give you a 6-input XNOR. So I gave you a bunch of 2-input XNOR, so you can gang up them like this. And you can, I also kind of show out here that why, for example, a structure like this is actually a 6-input XNOR. You sort of just some little mathematical analysis that you can go into that why it actually acts as that this whole structure is going to give you will be high if there are even number of ones.
If the input is not number 6 but number 7, so it's off.
If there are 7 inputs?
EFGs.
Okay, so there is one more. What you can do is you can have another XNOR gate and feed that, right? So you can have a G feeding into another XNOR gate out here.
But then if that's even, and there's another one that's going to be odd.
No, it will work out well, right? So let's think of it this way. So the question out here is, what if I had a G? So let's say I have a G. No, that's what I will do. Okay, and you can see that it works. So let's say this guy was high, and I've claimed that this stuff gives me is high when the number of things that were high here were even. Right? Now, when would this guy be high? For this guy to be high,
either 1 1 or 0 0.
either 1 1 or 0 0, right? So is my logic failing here? Let's see. So a 1 here indicates that an even number of A, B, C, D, E, F were high. G is 1. Let's see. You will need an XOR gate out here in this case. Yeah. Okay. So with OR, you will need an XOR gate.
But then again, if we have another one,
Another one that it got backwards now. So you have to.
you put G and
If you have a G and an H, then you can do the G and H as an XOR and here. So you have to just kind of do a little bit of further analysis. Okay, so let's look at, we have another 8-9 minutes. I wanted to yeah, this is the other problem I wanted to cover. So design a circuit that accepts 7 1-bit inputs A, B, C, D, E, F, and G, and it is going to output howsoever many of them are 0. So, so for example, if A, B, and C are 0 and D, E, F, and G are 1, then this guy should output 3 because 3 of them are 0. So the way I approach this problem is that actually I just realized that I forgot the inverters out here. Okay, so what you can do is you can say that the act of adding howsoever many are 0 is another way of saying is of the complement howsoever many are 1. Okay, so I first take the complement of A through G, and then really I just need to add them up, right? I mean, if 3 of the complements are high and the remaining are 0, if I add them up, I'm going to get the number of things which are high. In the worst case, all the complements may be high, which means all the original inputs were 0, which means I'll have a 3-bit number, 1 1 1. So really my problem fundamentally is to add 7 1-bit numbers. And the way to do it is I use 2 full adders to add A, B, C, and D, E, F. So that gives me 2 2-bit numbers. The sum output is in the units position in each one of them, and the carry output is in the 2's position. Now what I have is at this stage, I have 2 numbers which are in 2's position, and I have 3 1-bit numbers, namely the sum outputs of the 2 and this original G bar, which are in 1's position. I use a full adder to add them, take its carry out, and add with the other out here. And this would be my structure. And this guy is nothing but a 2-bit adder. So again, if I think in terms of the weight, all of these guys had a weight of 2 to the power 0. They are 1's position. When I added 3 of them, this guy has a weight of 2 to the power 1. This guy had a weight of 2 to the power 0. This guy has a weight of 2 to the power 1. This guy has a weight of 2 to the power 0. So next stage, I'm going to bring together those which have a weight of 2 to the power 0. So you would see that this full adder is taking the sum of the 2 full adders as well as this G. All of them have a weight of 2 to the power 0, so I can add them. I get this full adder. This guy will have a weight of 2 to the power 0, so that's S of 0. This guy has a weight of 2 to the power 1, the carry out. This full adder is now acting in the 2nd bit position. It's adding 3 bits, 3 1-bit things, each one of them with a weight of 2 to the power 1. So I get S1 and S2. This guy will have a weight of 2 to the power 1, and this guy will have a weight of 2 to the power 2. So that's my 3-bit number. So you could imagine variants of this problem where I ask you just count the number of ones, in which case you don't have to do that initial complement and other similar corrections. So we're adding a whole bunch of one bit.
This outputs the number of number of ones.
Huh?
This outputs the number of ones.
This outputs the number of ones in the complement, which is another way of saying is it's outputting the number of 0 in the original. Right? That's what the problem is. Any questions on this one? None? Okay. Let's see, which other problem that I didn't cover? Seven segment display. Any questions on that one? The TAs has covered it quite well. So hopefully. Decoder, 7 to 128 decoder. Go ahead.
I just don't, I'm not sure how to use the invert gate.
How to use the inverter gate in
There's
this?
nothing.
Okay. So actually, if you look at my solutions, I came up with, I described three possible solutions. The basic strategy in this thing is the following. You are given, you have 7 inputs, and I have given you 2 types of decoder, 2 and 3. So what you really have to do is you have to kind of break up 7 bits that you can feed into this. There are many ways I can do it. I can take 2 chunks of 3 and I have a bit remaining. I can take 3 chunks of 2s, I have a bit remaining. I can take 3 and 2 pairs, and then I'll get my 7. So I solve it all the 3 ways. So let's look at the approach where I took my 7 bits, I fed them into 2 3s to 8 decoders, and the remaining bit, I basically feed it into a 1-bit decoder, right? Which is essentially an inverter and the original bit. And then I have a group of 8 bits, a group of 8 bits, and a group of 2 bits. And I have to find all conjunction over it where one signal, all 3 input AND gates where one signal is drawn from group 1, another from group 2, and another from one of these 2. So I will have 8 times 8 times 2, that's 128 combinations.
I guess my problem is I know how to choose simply 331, 223, 331, or a lot of different combinations, but I don't know how to draw the wirings down there.
Well, so
I know we will have like 128 AND gates.
So see how I have drawn the wiring, right? What I did was I drew the groups and I show some samples. So like in this one, I'm saying take X7, take Y3, and take X3. And that results in output number 127 in my case. Okay. So what I did was I drew first one and then kind of dot, 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 and the last one. So you don't have to draw 128. I don't expect that.
So we always first decrease the most outside one. We go from the highest bit to the lowest bit.
You can go the other way around. That's fine too. It has to be in some order.
So did you just have 7 inverter gates instead of your 3 to 8, 2 to 4, and 2 to 4?
Oh, okay. So I could certainly do 7 inverter gates. The problem is now I have 7 groups, right? So I will need AND gates which are 7 input AND gates. And you could see that already in this approach 1 had 3 groups, so it needed 3 input AND gates. Approach 2 also needed 3 input AND gates. I have approach 3 where I use 3 2-input decoders and one. Now I have 4 groups, so I need 4 input AND gates, which is costlier. Okay, even though in context of this problem, since I counted an AND module as an AND module only, so it really didn't reflect this way, but in reality, 4 input AND gates are 30% more expensive roughly than a 3 input AND gate. But we certainly could do your approach. You have this huge AND gate.
For example, for B127, why is it not connected to the line for the inverter, but it's connected to the line that's not the inverter?
Yeah, because you can think of this as a group, and I have to select one wire from that group, either X or X1, right? This inverter plus the pass-through is nothing but a 1-bit decoder.
Yeah.
It's basically telling me whether input is 1 or 0. And I have to select one of them. From each group, I select one.
So you can select either one. You just change the one.
Well, you have, so again, I have a group of, I think I have not drawn this thing correctly out here. Shoot. I have to fix it. I'll have 4 wires here, 4 wires here, 4 wires here, and I have 2 in this group. So I have 4 times 4 times 4 times 2.
Can we do A1 instead of A0?
You have to do all the combinations. Okay?
But it's the same element doesn't matter. For 127, we choose X3, Y3, Z3.
Well, I mean, that would matter because for 127, I need to make sure that it corresponds to everything being 1. Right? So you have to select the right. Okay, so we'll stop out here. So again, extra office hours today as well as tomorrow.